Yeah, thanks very much for the opportunity to present this new experiment that we are at the moment constructing here in Mainz. And it's another experiment to search for axions, very much in the way that we already heard just now. And this is in close collaboration with Rades, and we got a lot of help, in particular from Jessica. So why axions? This was already a bit discussed. I just wanted to point out that they are really, really likable and very popular at the moment. So popular that if you look at this website here where you can get these nice plush toys, they're actually out of stock since quite a while and probably will continue for a bit like this. So we already heard they can clean up the strong CP problem. Then they appear in many BSM theories. So all string theories, grand unified theory, even SUSY would have axions or at least axion-like particles in there. And then, as we already also heard, they can be dark matter, which is pretty fascinating. So how can that be? I don't go into the details here. This was already discussed and will be discussed much more during the week. I just want to mention that, or point out that they will follow Bose statistics. So an ensemble of even very light axions can act as wave-like, macroscopic wave-like dark matter. And there are bounds on the masses what the axions can have. And they have to be at least about 10 to the minus 22 electron volts. Otherwise, the wavelength will be so large that they cannot contribute anymore to the structure formation in the universe. And they should be lighter than about 10 to the minus 2 electron volts. Otherwise, the measured neutrino flux from SN 1987 would not match with the models what the neutrino flux is predicted. So, assuming that all of dark matter is QCD axions, then one can start building models and see what would be the mass, probably. This depends a bit on the production mechanism, and it is extremely difficult to calculate, in particular if the axions would be generated in strings or domain ball. So there's no ab initio calculation possible. We end up with several models. And some of them are listed here on the summary plot. And you can see they span quite a range in masses, but they cluster around this range from micro electron volts to milli electron volts. So this is one of the interesting ranges to look for axions. And then you see there's also a lot of experiments, while this yellow band here corresponds to the QCD axion. And there is one new result that I was asked to point out. This is the cast Rades run that was recently published, the first physics run of Rades. This is right here. And this is in a very similar range where also our experiment would sit. So how is this done? This was already mentioned. So axions convert in a strong B field with a virtual photon from the B field just to a real photon. And this can be resonantly enhanced in a cavity that one puts into the magnetic field, and then one reads out the RF power from the cavity. One expects the resonant peak just from thermal noise of the cavity, and on top a narrow axion signal. And the masses of the power of the axion signal is typically in the order of 10 to the minus 24 watts. To cover a range of only 3 orders of magnitude, like from micro electron volts to milli electron volts, one already needs various designs of the cavities, because one cannot simply tune a cavity over this huge range. So this is why we have these plentitude of experiments here. And we are going to set ourselves right here in the order of starting at 8 gigahertz and beyond that. So what do we want to do? Well, where can we improve? If one looks at the signal power that is generated from the axions in the cavities, then this scales with B squared, and we're going to have a 14 Tesla magnet available here. There are plans, not in Mainz, but in general there are plans to go up to 20 Tesla magnets, but this is still a bit in the future. But however, large fields mean smaller volumes. This volume goes linearly in this equation. This is limited by the magnet aperture naturally, but also by the resonance frequency and the tuning elements. And then one has the quality factor Q0 here, and this depends on the material of the cavity. So for high purity copper, one achieves 5 times 10 to the 4. If one now uses superconducting cavities, one can go higher, and the target is about 10 to the 6, but this is very difficult in high magnetic fields, because if you put a superconductor in a high magnetic field, at some point superconductivity breaks down, and even if this is not the case, you can still have losses introduced due to vortices that move through the cavity, which limits your quality factor. What was demonstrated was by the CAPP collaboration. They used a high temperature superconductor and reached values of up to 3 times 10 to the 5. And then Jessica with Rades together, they used a different high temperature superconductor and achieved in the order of close to 10 to the 5 on the quality factor. Now there is more materials that can be studied. Of course, niobium-free tin is interesting. There are further high temperature superconducting. So this is quite a growing field, and this is something where we want to contribute also here in Mainz too. So the setup that we are currently constructing looks like this. We have the 14 Tesla magnet here inside, at the moment, just the liquid helium cryostat at 4 Kelvin, which can be pumped so that we can go down to 2 Kelvin. And then the cavity sits in here. We have a cryo preamplifier, and then a warm room temperature preamplifier, and then we go to a spectrum analyzer. The inner bore of the magnet is 9 centimeters, and the useful diameter in our cryostat is 5 centimeters. And then the preamp we have is a standard HEMT preamp, and at 10 gigahertz it has 36 dB gain and effective noise temperature of just below 4 Kelvin. So we constructed a cavity which just fits in this magnet inside. That's the design of the cavity here. See a picture of it. We tuned the antenna length in simulation, so we just sit on the critical coupling, and it turns out that this worked quite nicely. So this is in yellow the simulation of the S12 parameter of the cavity, and in blue the measurement. And we are just about 5 megahertz away from the predicted frequency, and the quality factor Q0 is also quite close. It's 16,000 at room temperature compared to 18,000 for the pure copper cavity. So if you then go to 4 Kelvin without the superconductor, we expect a factor of 4 improvement to 65,000. And then on top of this, we would, once we have the cryostat, start looking into the superconductors. So the readout is shown here very briefly. So we start from the cavity, then we have an isolator in the cold volume which would kill all the reflections from our preamp, then the preamp in the cold volume, the second warm preamp, and the real-time spectrum analyzer. We read out with a bandwidth of up to 40 megahertz in real time. At the moment we use 10. The acute data is streamed to PC, where it's converted to the frequency domain with a 1 kilohertz readout bandwidth. And then the data is stacked in 2 seconds. And this is done, is ready, and we tested it quite extensively. And we can continuously record data here. And then the later on analysis is based on Python, where we do further alignment of the data, the gain curve elimination, and eventually fit the resonance structure of the cavity. So what's the performance of our readout chain? This shows the gain curve of our preamplifier in blue, the cryo preamp plus the real-time spectrum analyzer, and in yellow only the spectrum analyzer with its preamplifier. And you see quite a lot of structure here, but actually it's very small, so the small scale fluctuation is only 0.2% on the pedestal, and the full range is still below 1% on the noise pedestal of the readout chain. And this is with an integration time of 1 hour, all at room temperature at present. We found some hiccups there, so when we check how the RMS of the noise scales over the integration time, then we expect this 1 over square root of time dependence in blue here. What we saw initially was this yellow curve with these nice edges and really surprising steep drops. And this was with the provided software by the manufacturer. And it turns out that they do automatic adjustments of parameters that they don't tell us about. If we write our own software, then actually it looks pretty perfect. So this is time in seconds. So this is up to half an hour. The noise falls exactly as expected, which we were very happy about. Then this is now the cavity that I've shown you before, again at room temperature, just attached to the readout chain. And you see in blue here the raw data that is recorded. And if we cancel out the gain curve of the readout chain, then we end up with the yellow curve. Then if you look at this a bit more detail over time again, then you see in blue here, this is the peak position of each of the 2 second blocks, and it moves around quite a bit, up to 170 kilohertz in about 2 hours, which we attribute to small temperature drifts. But this can be easily corrected for, as we in each 2 second block can fit the resonance shape we can correct for the peak position afterwards. In the in the yellow dots here, you see the RMS of the spectra of each of these 2-second blocks. And you see in the beginning here, we had probably a wrong setting on our spectrum analyzer. So this is a very good tool to see if the quality of the data is consistent and okay. If you do the integration, we end up with the resonance curve. Then we can fit it with Lorentz, and what remains afterwards is the residual here. It's essentially a non-corrected structure of the gain of our readout chain. And this is quite small. If you compare the size of this, it's on the same scale as the full peak. It's about 10 to the minus 3 of the height of our peak that we have. Then we can start injecting a signal and see if we would actually see it. So this here is the axion signal that we injected. It's about 1% of the noise from the cavity. And then we do the same again. We do all the corrections. We fit the Lorentz peak of the cavity structure. We use it, and here's a super nice signal. Okay, this would be nice if we really would see it in reality at some point. So this is again the residual of the measurement, and then we can do a peak finding algorithm on this, and this is what comes out. So here we see the noise after the peak finding, and here a proper peak, and then this can be used afterwards to statistically see how sensitive we are. So how sensitive do we expect to be once we have the cryostat and we are cold? So this is the plot that was already shown sometimes with the various experiments. We're going to sit close here at 8 gigahertz, and this is our expected limit for this first cavity that we have, where we measure just at a single point, and we can integrate for hours, many hours. So if you integrate for a day, then we end up down here. This is the blue spot. If we then move to tunable cavities and we try to do a measurement with a scanning speed of about 1 hour per megahertz at 4 Kelvin, then we end up with the green part here, so which would be in this range here. And this assumes that our cavity has a quality factor of 10 to the 5, which seems reasonable, and with the volume of our prototype cavity. So to give you a bit of an outlook, the setup that we're building is expected to have very fast turnaround times. We should be able to cool down the cryostat in half a day with a very easy installation of the cavity, because we don't have to open everything. It's just a top loader cryostat. So it's a very good setup to do R&D on these cavities once we go to the superconducting cavities. And this is what we want to do. So within the Readout collaboration, we want to study the behavior of superconducting cavities in the 14-Tesla magnetic field. And the first superconducting radio frequency cavity is expected to arrive here in fall. Then, of course, we move to tunable cavities, and eventually, once the magnet and cryostat is operational in fall, we want to take first physics data at the end of the year, hopefully, and then have the first physics result early next year to be published. And this is all I want to tell you about this new setup that we're currently constructing here. Thank you very much.
Thank you for the very brilliant talk. Tomorrow, Dano and Mr. Dano is going to present the new data from CMD about the superconducting.
Yeah, I'm very much looking forward to that.
Any questions?
Can I ask a very technical question? I was a bit surprised by its manufacturer's software. Is it a Tektronix spectrum analyzer?
Yes, yes it is.
Is it like an FFT development, right?
Sorry?
Is it an FFT or something in a development buffer?
Exactly.
Yeah, because it looks very funny, because there is certainly a peak around like 600 seconds. After that, it's kind of approaching to the profile.
Yeah.
Do you know what happened inside that software?
So what we know for sure is that they do a phase alignment of the input stage whenever they seem fit, and we can't control if we use their software. But this probably explains the kink that what you saw before is So that it flattens out here up to a pedestal, then gives a kink, is probably the phase alignment. Why it then drops faster than we would expect, I have no idea. So this was very strange to see this.
So when you solve this problem, you read out directly the data from this device,
Yeah.
or use the IF output and the digitalization outside. So you read out the data. So what is the data buffer size of this device? Because this will eventually limit how long time you can implement.
No. So with up to 40 megahertz, if the readout PC is fast enough, it can continuously stream. It does not buffer internally. It has a few hundred megabytes of memory, and if we read out with the custom software, then also this will limit to 2 seconds. That's actually why we have the 2 seconds blocks. Then the buffer is full. If we read out the IF data, actually what is read out is not the IQ, it's even the IF data directly. This can be really streamed continuously forever. The only thing is, when we set it up, we have to configure the device, do the phase alignment. At that point, the calibration constants are stored, and then we read the data. So we don't want to do this too long. We want to, in between, let the device do its recalibration. But up to an hour, we also tried up to 2 hours, it seems real good.
Thank you.
Any question? Or, yeah, yes. So I have a question for myself. So can you go to like the bottom in quality factor of like different gravity? Like what about I think it's slide number 3, I think. On 4. Yeah, this one. So you have a quality factor. This is non-tunnelable cavity, right? This is a non-tunnelable cavity. There's no tunnel in this cavity.
Yes. So the results that are shown here is all from non-tunable cavities.
So if you put like the cleansing or the turning mechanism work, the quality factor drops significantly, wouldn't it?
That depends on how you do it. So these cavities are rather small, right? So they are 3 by. So the idea is that we actually would open the whole cavity. So we would not put a rod inside, but we would really change the dimensions of the cavity for tuning. And then it depends a lot how you make the gaps, how you manage to get the superconductor over the gaps while tuning. So this is still a not trivial problem.
So in this case, we are not like adding the rod in the other movie or having.
No. Yes. Exactly.
Thank you very much. I think we conclude by the second topic.